Hi everyone. My name is Guillaume Charavel. I am an experienced Python developer, but I'm fairly new to the world of machine learning. So keep that in mind for the next 10 minutes or so, and I'll be presenting you things that I just learned. I had the great opportunity to join P16 and in RIA last June to maintain a Python library called tslearn, which has been developed by Romain Tavenard, professor at Rennes 2 University. Please raise your hand in the audience if you're the creator of tslearn. Thank you, Romain. I might need you for the Q&A session. So, what's tslearn? As I said, it's an open source Python library that is based mainly on scikit-learn, on the almighty scikit-learn, but not only. It's an open source project. You got the link to the GitHub repo here, where hopefully you'll find all the relevant information for a pleasant journey into tslearn. The probable most relevant one being the link to the documentation. And we hope to see you there, all of you, pretty soon. Current Python package is 0.64, actively developing 0.7, 0.7 now, and you can have it through PyPy, or you can use a Conda installation through the Conda 4 channel. So that's for the packaging. Let's look what's inside tslearn now. As I said, it's a machine learning toolkit for multivariate variable length time series. Let's focus 1 second on the characteristics of time series. They are three-dimensional, so one dimension being the number of time series, one dimension being the number of points in the time series, one dimension being the number of features for each point in the time series. They also are subject to time distortion, like acceleration and the shifts. And as I said, they might be of variable lengths. The features that are included in tslearn are basic input formatting. We, under the hood, use non-padding for variable length time series. So you got utilities to format your data. You also got utilities to generate like dummy data sets for fast prototyping. We also have some methods to fetch online data sets. Quite classical ones. We provide preprocessing that are dedicated to time series, imputation, resampling. We got scalars. We've added some of them recently, so hopefully fits your needs. We got metrics, and that's the heart of what tslearn has to offer. These metrics will have an example of why use dedicated metrics later, but these metrics are the core of tslearn. Sorry, we got GTW, longest common sum subsequences, extra. Clustering, regression, and classification algorithms that are either known algorithm but tuned for the specific usage for time series or specific algorithm. If you're familiar with all what I said, great. You're just one pip install away from experiencing with tslearn. Otherwise, I hope the documentation has everything you need. So why use tslearn? Well, we'll focus on why. What are the drawbacks if you don't? Here is a basic example of a clustering task. You've got the data set in the graph, in the bottom graphs. Here the time series lie in the one-dimensional feature space, and they all have the same length. So basically there is no problem with the formatting of the data. But if we feed the data to classic sklearn, k-mean clustering estimator, we end up with a classification, clustering that is at least dubious. We can see that we have on cluster 2 and cluster 3 some time series with peaks that are distributed in two clusters. We might want them to be categorized together. And also the red lines, which represents the barycenters of the cluster, have interesting shapes. Spoiler alert, the underlying problem here is that we use a sequential point-to-point metric, some Euclidean distance. And so how we can do better? Maybe we can use time series metrics, so they are less prone to time distortion. In this case, I'll focus on DTW, which stands for dynamic time wrapping. That's, as I said, the metrics are the core of tslearn, and that's one of the metrics we provide. I'll try to make myself clear, I'm not sure. So here we want to compute an optimal alignment for the two time series that are depicted on the left of the diagram and on the top of the diagram, the blue lines, with under some constraints, of course. The first 2 points has to be aligned together. The last 2 points has to be aligned together. There is no going back in time. So if you've aligned point E of first time series with point G of the second time series, point E plus 1 should be aligned with shouldn't be aligned with something that is before point G in the second time series. And you can align 1 point to one or more points of the other time series. Hence, the fact that we support variable length time series with this particular metric. The square image here represents the cost matrix. Each point of one time series being assigned to all, being aligned with all other points of the second time series. The brighter the color, the further away the points are. So basically what we are doing here is that we are finding an alignment that is dependent on the content and not static as it was before. And here we can see that the optimal path is depicted in white in this example. And therefore, for example, the two peaks are aligned together, and the flat part of the time series that stands between the two peaks is kind of aligned together too. DTW gives you a similarity score between these two time series as well as the best alignment path. So what happens when you use these metrics inside standard k-mean algorithm from tslearn? Then you got this kind of clustering, which is, in my point of view, better, but still I don't have much experience. First cluster groups all the peaky time series, and the shapes of the barycenters are, well, they feel better. And also the flat ones in cluster 3, the flat type series cluster 3, they are now grouped together and they pop. So that's great. That's an example of why use dedicated tools for time series. As I said, tslearn is based on scikit-learn, and we benefit from all the great features in scikit-learn. Like this is an example just to show you that this is pure scikit-learn syntax with grid search, cross-validation, and a pipeline fed with tslearn estimators. Just to show you that it's basically pure scikit-learn syntax. And of course, as you may expect, you benefit from the cross-validation results and the best params through scikit-learn features. Yeah, just wanted to focus for a minute on the learning shapelet estimator. That's something I've been working on lately, and here the idea is just to learn some small shapes that perform the classification of the train data train optimally. The hyperparameters here are the number of shapes you want, and that should be 2 in this example, and the length of each shape, that's 20. And yes, it's the other way around, but still works. Not going into much details, but here the idea that the algorithm will learn the best shapes for this particular data set. Just showing some results here and visualization with the 2 shapelets that were learned on the top left, the classes and the classification boundaries, just to see that it works great. And yeah, as I said, I've been working on this, and I've added the support for variable length time series. So that's cool. What's next? We have a lot of things to do. We'd like to join the Array API trends. So for you not familiar with it, it's some kind of, it's a way to be agnostics from the input. So you can use whatever array library you like for the inputs, and that's important because you can integrate with a lot of different libraries. We want to add more estimators, of course. We want to add some basic forecasting, GPU computation, optimization, refactoring, etc., etc., etc. So there's a lot to do, and we welcome newcomers. So if you want to have a look at tslearn, and yeah, be welcome to visit the repo, and that's where we can interact together. tslearn has an academic inheritance, so we welcome citation. And that's basically it. Thank you.